Hello guys, this is Vince Nass from the class of Software Engineering in Masters in IT. Now, for this chapter, chapter 13, we will be talking about security engineering. Now, in security engineering, there will be security, dependability, security and organizations, security requirements, secure system design, and security testing and assurance. Now, in security engineering, there are tools. It can be a hardware, a software, techniques, and methods. Any methods like algorithms to support the development and maintenance of the system so that the system can resist any malicious attacks that are intended to damage the computer-based system or its data. It is a subfield of a broader field of computer security, in which we will be digging deep on the security of the computer. Security has its dimensions. Confidentiality. Information in a system can be disclosed or made accessible to people or programs that are not authorized to have accessing that information. In short, information has its own limits. Integrity. Information in a system may be damaged or corrupted by making it unusable or unreliable, in which this integrity, any information is very vulnerable to be destroyed or be corrupted. Availability. The access to a system or its data that is normally available may not be possible. In which, in here, in availability, we can determine if the information to the system is only made public or private. Now, in security, now have the levels. Infrastructure security, which is concerned with maintaining the security of all systems and networks that provide an infrastructure and a set of shared services to the organization. The security is now focused on everything in the organization. Next, application security, which is concerned with the security of individual application systems or related groups of the system. Here, security is focused on the child systems of the main system. Next, operational security, which is concerned with the secure operation and the use of organization systems. Here, in its word, security is focused on the systems that makes other systems operational. Now, from the system, we have now the layers where security may be compromised. From top to bottom, we have the application. Next are its reusable components and libraries, the middleware, database management, generic shared applications, alright, like the browser, email, etc., the operating system, and the network and hardware. Application security is a software engineering problem where the system is designed to resist attacks. In the meanwhile, infrastructure security is a system management problem where the infrastructure is configured to resist the attacks. Here and there, in this chapter, we will be focusing on the application security rather than in the infrastructure security. System security management. Here, we have the user and permission management, where we add users or remove users from the system and setting up the appropriate permissions for the users. It's like classifying users, being admins, guests, or any VIP users. Second, we have the software development and maintenance, where here we're installing application software and middleware and configuring the system so that vulnerabilities are avoided. In here, we are configuring these applications to see whether they are very vulnerable to attacks or not. Third, we have the attacking, monitoring, detection, and recovery. We are now monitoring the systems here for any unauthorized access, the design strategies for resisting attacks, and developing the backup and recovery strategies. Operational security. It is primarily a human and social issue, in which that this operational security is concerned with us users, like concerned with ensuring the people do not take actions that may compromise the system security, like setting passwords, leaving computers logged in, or maybe making someone use your account. That's not it. Here, users sometimes take the insecure actions to make it easier for them to do their jobs. Therefore, a trade-off between security system and system effectiveness is getting revoked. Security and dependability. Security. The security of a system is a system property that reflects the system's ability to protect itself from any accidental or deliberate external attacks, where security can be concerned from accidental, accidents may happen, or deliberate external attack from someone or any softwares. Security is essential as most systems are networked so that external access to the system through the internet is made possible. Yes, because systems today are made networked. You know what they say? Networked means that every computer may connect to you. So we should have the security for us to be protected from any threat of an unknown computer. Security is an essential prerequisite for availability, so that it's very available, reliability, we can rely on them, and safety, so that we don't get hurt. Now we have the fundamental security. If a system is network system and is insecure, then statements about its reliability and safety is very unreliable. How can we say that a system is very reliable if it is very easy to get in, right? In a network system. Now, these statements depend on the executing system and the developed system being the same. However, intrusions can change the executing system or its data. Therefore, the reliability and safety assurance is no longer valid. Now, we have asset. What is asset? It is something of a value which has to be protected. The asset may be the software itself, the system itself, or the data used by that system. It is something that is very valuable, very important to the system, that should be protected. Attack. An exploitant of a system's vulnerability. Generally, this is from the outside of the system and is deliberate attempt to cause more damage or cause some damage. Control. A protective measure that reduces the system's vulnerability. Encryption is an example of the control that reduces the vulnerability of a weak access control system. Exposure. Possible loss or harm to the computing system. This can be a loss or damage to the data, or can be a loss of time and effort if recovery is necessary after a security breach. Threat. Circumstances that have potential to cause loss or harm. You can think of this as a system vulnerability that is subjected to an attack. Vulnerability. It is a weakness in a computer-based systems that may be exploited to cause loss or harm. Here, in vulnerability, it is how we can say that a system has its own hole. Here are some examples of the security terminologies. The assets. An example of that is the records of the patients or the rest of the database, the data itself inside the database. Okay. Exposure. Potential financial loss from future patients who do not seek a loss of reputation. Vulnerability. A weak password. which can be makes easier for any users to guess an attack, an impersonation of an authorized user. Threat. An unauthorized user will gain access to the system by guessing the credentials, login, name, and password of any unauthorized user. And there's the control, a password checking system that this allows user passwords that are proper names or words that are normally included in a dictionary. Now we have the threat types. First, there's the interception threats. It allows an attacker to gain access to an asset, something that the attacker can get inside the system to get something valuable or destroy that something valuable. Second, we have the interception threats. It allows an attacker to make part of the system unavailable, in which this can sever the connections from the database server, uh, other people from getting in the system, or something that it can block any users from the system itself. We have the modification threats that allows an attacker to tamper with the system asset. Here, the attacker can tamper with the data or any valuable information of the system itself. Next, we have the fabrication threats that allows an attacker to insert false information into the system. Here, the threats can give out any, let's say, different datas or some false information that is not in the system itself. Now we have the security assurance. Vulnerability avoidance. The system is designed so that vulnerabilities do not occur. For example, if there is no external network connection, then the external attack is impossible. We have the attack detection and elimination. The system is designed so that the attacks on vulnerabilities are detected and neutralized before they result in an exposure. For example, we have the antiviruses or any malware, anti-malware softwares. We also have the exposure, limitation, and recovery. Here, the system is designed so that the adverse consequences of a successful attack are minimized. For example, we have the backup possibility. For example, the data is destroyed or the data is being tampered. We can restore it from its previous very recently backup data on the system. Here we have the security and its dependability. The security and reliability. If a system is attacked and the system or its data are corrupted, then as a consequence of that attack, this may induce the system failures that compromises the reliability of the system. System security and availability. A common attack on a web-based system is a denial of service attack, where the web server is flooded with many service requests from a range of different sources. The aim of this attack is to make the system unavailable. Here, it's like from a web server, a flood of different users is being entered, being entered on a website continuously, so that the website or its hosts are being flooded with so many users that the server itself might crash down. Security and safety. An attack that corrupts the system or its data means that assumptions about safety may not hold. Safety checks rely on analyzing the source code of a safety critical software and assume the executed code is completely accurate translation of that source code. If this is not the case, then safety related failures may induce the safety cases made for the software is invalid. Security and resilience. Resilience is a system characteristic that reflects its ability to resist and recover from damaging events. The most probable damage event on a network software system is a cyber attack of some kind, so most of the work now done in resilience is aimed at deterring, detecting, and recovering from such attacks. Security and organizations. Let's focus security as a business issue. Now, security is inexpensive and it is the most important that the security decisions are made in a cost effective way, meaning that security must be cheap but very effective. Organizations use a risk based approach to support the security decision making and should have a defined security policy based on security risk analysis. Security risk analysis is a business rather than a technical process. Organizational security policies. Security policies should set out general information access strategies that should apply across the organization. The point of security policies is to inform everyone in an organization about security so this should not belong and the detailed technical documents. From a security engineering perspective, the security policy defines in broad terms the security goals of the organization. The security engineering process is concerned with implementing these goals. Security policies. The assets that must be protected. It is not cost effective to apply stringent of security procedures to all organization assets. Many assets are not confidential and can be made freely available. The levels of protection that is required for different types of asset. For sensitive personal information, a high level security is required. For other information, the consequences of loss may be minor, so a lower level of security is adequate. The responsibilities of an individual users, managers, and the organization. The security policy should set out what is expected of the user. Example, strong passwords, logging out of computers after use, office security, and etc. Existing security procedures and technologies that should be maintained. For reasons of practical and cost, it may be essential to continue to use the existing approaches to security even where these have known limitations. Security risk assessments and management. Risk assessments and management is concerned with assessing the possible losses that might ensure from attacks on the system and balancing these losses against the costs of security procedures that may reduce these losses. In risk management, it should be driven by an organizational security policy. It involves preliminary risk assessment, life cycle risk assessment, or the operational risk assessment. The preliminary risk assessment. The aim of this initial risk assessment is to identify the generic risks that are applicable to the system and to decide the adequate level of security can be achieved at a reasonable cost. Cheap. The risk assessment should focus on the identification and analysis of high-level risks to the system. The outcome of the risk assessment process are used to help identify the security requirements. Design risk assessment. This risk assessment takes place during the system development lifecycle (SDLC) and is informed by the technical system design and implementation decisions. The results of the assessments may lead to changes to the security requirements and the addition of new requirements. Known and potential vulnerabilities are identified. We can see now here the objectives or the possible vulnerabilities of the system. And this knowledge is used to inform the decisions making about the system functionality and how it is to be implemented. tested, and deployed. Operational risk assessment. This risk assessment process focuses on the use of the system and the possible risks that arises from human behavior. Operational risk assessment should continue after a system has been installed to take account on how the system is used. Here, we're focusing on how the users or any people that uses the system. Organizational changes may mean that the system is used in different ways from those originally planned. These changes lead to new security requirements that have to be implemented as the system evolves. Um, in here, since we focus on the users, there might be changes because the users might use the system in different ways. So in here, we now get back to this to see if there are vulnerabilities on the different ways of the user to use the system. Security requirements. Security specification. The security specification has something in common with safety requirements specifications. In both cases, your concern is to avoid something bad is happening. We have the four major differences. Safety problems are accidental. The software is not operating in a hostile environment. In security, you must assume that the attackers have knowledge of the system weaknesses. Here, we assume that attackers are very knowledgeable and can detect your weakness of the system. When safety failures occur, you can look for the root cause or weakness that led to the failure. When failure results from a deliberate attack, the attacker may conceal the cause of the failure. Here, we should be, let's say, the failures. We will use the failure as an upgrade for the system itself. Shutting down a system can avoid a safety related failure. Causing a shutdown may be the aim of an attack. Shutting down the computer, meaning literally turning off of the computer. If the computer is turned off, then the system is not operational. Safety related events are not generated from an intelligent adversary. An attack can probe defenses over time to discover weaknesses. We can say here that any attackers have all the time to know or found out the weakness of your system. Now have here the types of security requirements: identification, authentication, authorization, immunity, integrity, intrusion detection, non-repudiation, privacy requirements, security auditing, and system maintenance security. Security requirement classification. The risk avoidance requirements set out the risks that should be avoided by designing the system so that these risks simply cannot arise. Risk detection requirements define the mechanisms that identify the risks if it arises and neutralizes the risk before losses occur. Risk mitigation requirements set out on how the system should be designed so that it can recover from and restore the system assets after some loss has occurred. Here is a diagram of the preliminary risk assessment process for security requirements. We have the asset identification, can go to the asset value assessment, to the exposure assessments, and lastly to the security requirement definition. Or the assessment identification can identify the threat identification to the attack assessment and go directly to the security requirement definition. Or from the attack assessment, it can go from the control identification, then defining the feasibility assessment, then going to the security requirement definition, in which we now define on how the security measures is being made. to the system. Asset identification. We identify the key assets or services that have to be protected, in which here we identify what are the most important assets that should be protected inside the system. The asset value assessment. We estimate here the value of the identified assets in asset identification. Here, we give the value, for example, this asset should have the highest priority, this one is in middle priority, and this one in a lower priority. Exposure assessment. Here, we assess the potential losses associated with each asset. And we have the threat identification, in which we identify the most probable threats to the system assets. Attack assessment. We decompose the threats into possible attacks on the system and the ways this may occur. Control identification. We propose these controls that may be put in place to protect an asset. Feasibility assessment. We assess the technical feasibilities and the cost of the controls. And lastly, we have the security requirement definition, in which we define the security requirements. This can be an infrastructure or an application system requirement, meaning this system requirement can be from a smaller scale, a part of the system, that's why it's an application system, or everything on the system, which is the infrastructure system. Here is an asset analysis in a preliminary risk assessment report for the MenCare system. And here we have the threat and control analysis in a preliminary risk assessment report. Here is an example of the security requirements for the MenCare system. Misuse cases are instances of threats to a system. Interception threats. The attacker gains access to an asset, where an attacker can get inside the system, gets very near to something very valuable to a system or very important to the system itself. We have the interruption threats. The attacker makes part of a system unavailable. For example, the attacker might sever the connections between the user and the system itself. Modification threats. The part of the system asset is being tampered with, or being corrupted or modified, in which it changed. Then there's the fabrication threats. False information or changing of information itself in the asset of the system. It's an example of a misuse cases. Let's say that the left part is the user and the right part is the attacker itself. The middle part, the balloons there are the system itself. The user can register the patient, unregister the patient, view the patient information, transfer data, or contact the patient itself. The attacker can impersonate the receptionist, in which that he can go inside the system as a receptionist, as the user receptionist itself, or it can intercept its transfer of data to the database itself. Here is an example of a MenCare use case in transferring data. An example of a MenCare misuse case in intercepting the transfer. And the misuse case in intercept transfer. Secure systems design. Security should be designed into a system. It is very difficult to make an insecure system secure after it has been designed or implemented. Architectural design. How do the architectural design decisions affect the security of a system? Good practice. What is accepted as good practice when designing secure systems? Design compromises. Adding security features to a system to enhance its security affects other attributes of the system. The performance. The additional security checks slows down a system, so its response time or throughput may be affected. Usability. Security measures may require users to remember information or require additional interactions to complete a transaction. This makes a system less usable and can frustrate the system users. Design risk assessment. Risk assessment while the system is being developed after it has been deployed. More information is available. System platform, middleware, and the system architecture and data organization. Vulnerabilities that arise from design choices may therefore be identified. Here is a diagram of a design and risk assessment. In system requirements, we go to the system design. The system design can either go to the technology choices, where we pick the hardware, the architectural design, where we choose the design of the system, and these design assets. Then the tree goes directly to the design risk assessments. Then from that, the design risk assessment designs now the design and required changes to the system, and going back to the system design. Protection requirements. Protection requirements may be generated when knowledge of the system representation and system distribution. Separating the patient and treatment information limits the amount of information, for example, the personal patient data, that needs to be protected. Maintaining copies of records on a local client protects against denial of service attacks on the server. Here is another design risk assessment diagram, where the design assesses the assessed value assessment to the exposure assessment, going to the design requirements changes, or the design assessed can go to the threat identification, to the attack assessment, to the control identification, and going to the design and requirements changes. Also, an attack assessment can go into directly to the control identification, to the design and requirements changes. The technology and architecture choices go from 3 blocks, going to the threat identification, to the attack assessment, or the control identification. Design decisions from use of COTC. The system users authenticate using the name or password combination. The system architecture is a client server, with clients accessing from the system through a standard web browser, and the information is presented as an editable web form. Here is a sample diagram of the vulnerabilities associated with technology choices. From a technology choice, login or password authentication, the vulnerability is that users might guess the password. Yes, it is possible that anyone can guess your password. Authorized users reveal their passwords to unauthorized users. Some people might, let's say that they can trust anyone, so they give their own passwords. That's a vulnerability. Client or server architecture using web browser. The server is subjected to a denial of service attack, meaning it can sever the connections between the user and the system. Confidential information may be left in the browser cache. Yes, in browsers, we have the histories, the caches, and let's say in accessing browsers, you might access something of a very important, and it might get in the cache or the memory, small memory of the web browser. Okay. Also, a vulnerability is that the browser security loophole lead to unauthorized access. Yes, in browsers, we have also the security measures because not all browsers are very secure. Use of editable web forms. File graining, logging or of changes is impossible. Also, authorization can't be varied according to the user's role. Now, a password checker shall be made available and shall be run daily. Weak passwords shall be reported to system administrators. Here, passwords is a very big issue. In the systems, password should be always being checked and always being upgraded into something that is very less vulnerable and less to be guessed by other people. Access to the system shall only be made by approved client computers. Okay, in systems, we have our users. Now, from the users, we have also the limitations. What are the only allowed users that can access the system? And what are the non-users that cannot be allowed in the system? All client computers shall have a single approved web browser installed by system administrators. The system administrators only gives them the proper only web browser to be used for the system. Now, the architectural design. We have two fundamental issues to be considered when designing an architecture for security. First is the protection. How should the system be organized so that the critical assets can be protected against external attack? Distribution. How should system assets be distributed so that the effects of a successful attack are minimized? These are potentially conflicting because if the assets are distributed, then they are more expensive to protect. If the assets are protected, the usability and performance of the requirements may be compromised. Protection. We have the platform level protection, in which the top level controls the platform on which the system runs. The application level protection, a specific protection mechanism built into the application itself. Example, password protections or any kind of software. Folder protection, folder passwords or like that. Then there's the record level protection. Protection that is invoked when access to a specific information is requested. Here, protection is, for example, when accessing any data, it should have the request to the admin if it has the permission to access that data. These lead to a layered protection architecture. Now here is a detailed diagram for the layered protection architecture. From the platform level protection, we have the system authentication, the system authorization, and the file integrity management. From the application level protection, we have the database logging in from databases. We have the database authorization, the transaction management, and the database recovery, backup systems. Below there, we have the record level protection, the record access authorization, read encryption, and the record integrity management. Now, below is an example of the patient records. Okay, now having finished of the protection, we now have the distribution. Distributing assets means that an attack on one system do not necessarily lead to a complete loss of system service. Each platform has a separate protection feature that may be different from other platforms so that they do not share a common vulnerability. Meaning, for example, this system is for web-based and this is for desktop protection. Let's say from different platforms, it has its different vulnerability. Now, in distribution, it is particularly important if the risk of denial of service is very high. Okay, this diagram is an example of a distributed assets in an equity trading system. Design guidelines for security engineering. Design guidelines encapsulate good practice in securing system design. Design guidelines serve two purposes. They raise the awareness of security issues in a software engineering team. Security is considered when design decisions are made. They can be used as the basis of a review checklist that is applied during the system validation process. Design guidelines here are applicable during the software specification and design. Okay, here in the design of the security, it is applied during the system validation because we cannot validate the system if the system itself is not very secured for its design. Here is the design guidelines for a secure system engineering. The security guidelines base security decisions on an explicit security policy. Avoid a single point of failure. Failure is not an option. Fail securely. Balance the security and usability. Log user actions. In logging user actions, we, for example, give the logbook or the output logs or of the users getting in the system or getting out of the system, or the actions taken by the users is recorded from the logs. Use of redundancy and diversity tool reduce the risk. Specify the format of all system inputs. Setting limitations. In specifying the format of all the system inputs, an example here is setting the limitations on how or what can be user input to the system. Compartmentalize your assets. Design for deployment and design for recoverability or backing up the data. Now, design guidelines. Base decisions on an explicit security policy, where we define a security policy for the organization that sets out the fundamental security requirements that should apply to all organizational systems. Avoiding a single point of failure. Ensuring that a security failure can only result when there is more than one failure in security procedures. For example, we have password and question-based authentication. Fail securely. When system fail, for whatever reason, ensure that sensitive information cannot be accessed by unauthorized users, even although normally security procedures are unavailable. Balance security and usability. We try to avoid the security procedures that make the system difficult to use. Sometimes you have to accept weaker security to make the system more usable. Log user actions. Maintaining a log of user actions can be analyzed to discover who did what. If users know such a log, they are less likely to behave in an irresponsible way. In user log actions, we can say that the logs are kept private. for the users not to know that there is a log inside the system. Use redundancy and diversity to reduce the risk. By keeping multiple copies of data and use diverse infrastructure so that an infrastructure vulnerability cannot be the single point of failure. Okay, now specify the format of all system inputs. If inputs formats are known, when you can check that all inputs are within range so that unexpected inputs do not cause problems. Compartmentalize your assets. We organize the information so that assets are in separate areas and users only have the access to the information that they need rather than all system information. Design for deployment. By designing the system to avoid deployment problems. And design for recoverability, where we design the system to simplify recoverability after a successful attack. Secure systems programming. Now, aspects of secure systems programming. Vulnerabilities are often language specific. Here, we can say that from the word programming, there are different kinds of programming. So vulnerabilities are often language specific. If the attack is from C++, then it's a C++ language. The system is a C++ language. If the system is in C, programming C, then the attack is in programming C. Now, security vulnerabilities are closely related to a program reliability, in which here, programs without array-bound checking can crash into actions taken to improve the program reliability, can also improve system security. Dependable programming guidelines. Number 1, we limit the visibility of information in a program. In programming, we only write the codes for functionality. We cannot, even there are comments, we cannot put valuable information inside the program itself. Number 2, we check all inputs for validity, in which that all inputs should be the same data type. Number 3, provide a handler for all exceptions. Number 4, minimize the use of error-prone constructs. Number 5, provide restarting capabilities, in which, for example, there's the system, if ever there are errors or an attack, then the system can automatically restart itself. Check array bounds. Include timeouts when calling external components, and name all constants that represent real-world values. We have the security, testing, and assurance. Now, testing the extent to which the system can protect itself from external attacks. The problems with security testing. Security requirements are shall not requirements. Example, they specify what should not happen. It is not usually possible to define the security requirements as simple as constraints that can be checked by the system. The people are attacking a system are intelligent and look for vulnerabilities. They can experiment to discover weaknesses and loopholes in the system. So, what are the security validations? We have the experience-based testing, in which the system itself is reviewed and analyzed against the type of attack that are known to the validation team. Penetrating testing. A team is established whose goal is to breach the security of the system by simulating attacks on the system. Those are sample hackers, white hackers, for example, that tries to breach the system to check its security. Or we have the tool-based analysis. Using various tools, security tools such as password checkers, are used to analyze the system in operation. And we have the formal verification, which the system is verified against formal security specifications. Here is an example of the entries in a security checklist. Okay, now here are some key points of the subject of security engineering. Now, security engineering is concerned with how to develop systems that can resist malicious attacks. We concentrate here on how to design a system or develop the system for it to resist any kinds of attacks. But we can say that no system no system can fully resist any attack. Security threats can be threats to confidentiality, integrity, or availability of a system or its data. Security risk management is concerned with assessing possible losses from attacks and deriving security requirements to minimize losses. To specify security requirements, you should identify the assets that are to be protected, the assets in which the important files or important data in the system that should be protected at all costs, and defined on how security techniques and technology should be used to protect these assets. Now, here are some other key points. Key issues when designing a secure systems architecture includes organizing the system structure to protect the key assets and distributing the system assets to minimize the losses from a successful attack. Security design guidelines sensitive system designers to security issues that they may not have considered. They should provide a basis for creating security review checklists. Then there's the security validation, which is difficult because security requirements state that should not happen in the system rather than what should. Furthermore, the system attackers are intelligent. They have more intelligence and more time to probe for the weakness or loopholes than is available for security testing. And that ends my presentation. Thank you very much for listening. This is Chapter 13, Security Engineering.